In this video, I'm going to do this exercise. So I have a set of three vectors that spans a vector space V, and I'd like to show that this new set of three vectors also spans V. So before I go ahead and write out this proof, I'm going to think it through, think about what I have and what it is that I need to prove. So this isn't part of my proof, it's just me thinking. Now the first thing is that my hypothesis is going to be that this set spans V. And so what that means is if I take some x in V, then there are scalars C1, C2, C3, and we're working over R, such that x can be written as a linear combination of V1, V2, V3. So we know that these constants exist. Now, we want to prove that this set spans V. So, in other words, we want to prove that for any x in V, that x can be written as a linear combination of these three vectors. So in other words, I want to prove that there are scalars alpha 1, alpha 2, and alpha 3 such that x can be written as a linear combination of the vectors in this way. So the vectors in this set. Now let's expand this, and maybe that will give us a clue for what alpha 1, alpha 2, and alpha 3 should be. So I've gone ahead and I've expanded this expression, and here's what I have. X is equal to that times V1, that times V2, and that times V3. All right, but I know already that there exist these specific constants, C1, C2, and C3, such that x is equal to this, right? So I can let this alpha 1 plus alpha 2 plus alpha 3 be C1, alpha 2 plus alpha 3 be C2, and alpha 3 be C3. So I've gone ahead and I've written that out, and now I can just solve for alpha 1, alpha 2, and alpha 3. If alpha 3 is C3, then I know that alpha 2 is going to be C2 minus alpha 3, which is C2 minus C3. And over here, alpha 1 is going to be C1 minus alpha 2 minus alpha 3. So I've gone ahead and simplified. So if I let alpha 1 be C1 minus C2, alpha 2 be C2 minus C3, and alpha 3 be C3, that will give me the correct linear combination. So I'm now going to go ahead and write out a nice proof. So just recall what it was that we were going to prove, where we've got that this spans V, and we want to show that this new set spans V. So I'm going to go ahead and prove that. And so the first thing we do is we always assume the hypothesis. So I've got my assumption that this set spans V. I want to show that this set spans V. And again, what that means is that every element in V can be written as a linear combination of those three vectors. So I should take some x in V, and I want to show that x can be written as a linear combination. And again, since that set spans, we know that x can be written as, we used C1 and C2 and C3 above, so we're going to do that here too. That's where these are specific constants, C1, C2, and C3 in R. Now I want to show that x can be written as a linear combination of these three, and I know what I should use for my coefficients. I should use that, that, and that. So let's go ahead and show that that works. So if I write alpha 1, so C1 minus C2 times V1 plus C2 minus C3 times that next vector, which is V1 plus V2, and C3 times that last vector, I should get X, and I should show that I get X. So let's go ahead and work this out. And I've collected like terms here. So the coefficient on V1, I have C1 minus C2 here, and I have C2 minus C3 there. So that's how I got that. And for V2, I have C2 minus C3 there, and a C3 there, a C3 on V2 there, and the last coefficient is C3V3. And now if I simplify that, what I get is C1V1 plus C2V2 plus C3V3, and we know that that is actually X from this part here. So that's equal to X. So we've proved that indeed that vector X that we pulled out of V can be written as a linear combination of these three vectors. And so that proves that that set spans V. And so I've written a closing statement here. Since we've written X as a linear combination of those vectors, we know that this set spans V.